Nowadays, demand of renewable energy sources are increasing in every country because if you take non-renewable energy sources like thermal power plant, nuclear power plant, etc., they are not good for environment and they can exhaust any time in future due to lack of fuels. But if you take renewable energy sources, they are not like that. They are good for environment and they can't exhaust any time in future. Among all renewable energy sources, solar energy is used in more applications like solar homes, solar street lights, solar vehicles, etc. because it's easy to install and it takes very less space and low maintenance. So here my idea is like all other solar applications like solar home, solar street lights, solar vehicles. Here I am taking solar water pumping system because we know water is required for drinking, irrigation, domestic use, for livestock, and for industrial use. So, water pumping has become an indispensable task in day to day life. If you run water pumping system with solar, then that can be a beautiful innovation. Actually, we have so many solar water pumping system, they are already existed now. But the problem with that solar water pumping systems are the output of the solar system is depending on irradiation and temperature. Actually, temperature and irradiation is changing with respect to time. They are not constant. But our load requires constant power. What is our load? Here I am taking water pumping system, right? So most of the water pumping systems use the motor, nothing but induction motors. That's why here also I am taking the induction motor as my load. So we already know induction motor or any load requires constant supply, constant power. But in our solar system, we are not getting the constant voltage or power. We are getting the variable power or voltage. If you take the morning 6 to evening 6, it will be increase, and at the afternoon you are getting the maximum power, and at the evening you will get the low power, and in night time it does not give any power to the load. That is the solar system. Okay, so here we have the two major drawbacks, that is we are not getting the constant power at daytime and also we are not getting the power at night time. So we need to eliminate these two drawbacks. So to eliminate the second drawback, nothing but that to give power at the night time, we need to go for other alternative, nothing but the other source. We have so many sources. You can take battery, you can take microgrid, like that. So if you have alternating source as battery, here my thought is in daytime we already get the power from the solar, right? So in that power we are storing in daytime. So in night time I can give this stored power to the our load. So like this I am thinking. But the problem with the batteries are there are many complications with batteries such as low life, hazardous waste, and you can see acid leakage in lead acid batteries. For these reasons we are not going to take batteries. We need to choose other alternative because battery have some drawbacks. So that's why I am looking for grid connected solar system. So here I am taking the grid. So I am simply eliminating the second drawback. So that is nothing but this nighttime drawback with this grid, because we can get the power from the grid at any time, right, to our load. Okay, but our main thing is we need to run our motor by using this solar power only. Whenever this solar power is not available, at that time only we need to depending on this grid. That is the main thing you need to know. Okay, at night time, at daytime also you are not getting the exact power required for our load in some cloudy conditions. In that time also we need to take power from the grid to match the load power. And first drawback is in daytime also you are not getting the constant supply, right? So to meet the constant supply or to meet the demand power, we need to use a MPPT technique with some boost converter. Why boost converter? Because in solar we are not getting the exact power what we required for our load, right? We are getting the low power. So to extract maximum power from the solar panel, we need to use the maximum power point technique with this boost converter. So by using these two devices, you can get the maximum power from the solar panel to meet the load requirement. Okay, because if you see this graph, from morning 6 to afternoon 12, you are not getting the maximum power, right? So whenever the irradiation temperature is high, At that point only you are getting the maximum power. Okay, in remaining time you are not getting the maximum power at morning and at evening also. So in that time you need to extract the maximum power whatever we have in our solar panel. So at this condition we can use the MPPT with our boost converter to increase the voltage level. So like this we can eliminate the first drawback also. So here we have so many of maximum power point trackings like incremental conductance, batter band absorb, and hill climbing system, and so many. But here I am preferring incremental conductance maximum power point tracking for our project. Why IC only? Because this maximum power point tracking is simple to handle and it has the good tracking efficiency. It also adjusts the step size automatically to reach maximum power point and improves the response under steady state and dynamic conditions. That's why I am taking the incremental conductance as our MPPT technique. But the thing is, we know this induction motor, that name indicates induction means it needs AC, right? But we are getting the DC as the output of solar cell. And after connecting this DC as input to boost converter, at the output of the boost converter also you are getting the DC. But our load or induction motor requires AC, right? So to convert this DC to AC, we need to connect a one DC to AC converter, nothing but inverter. Okay. So after connecting this inverter, then you will be able to get the DC to AC and you can give this AC to your induction motor. That's it. So here I am using the 3-phase inverter because our load is 3-phase induction motor load. So why inverter here? To convert DC to AC we are using the inverter here because our induction motor needs AC only, not DC. Okay. And the other thing is coming to grid. This is the alternative source, right? In night time, or if you are not getting the exact power from the solar, you can use this grid. Okay. In grid, you are getting the AC, right? So to connect this grid with this solar system interlink is DC, right? But here we are getting the AC only. Okay, in grid we have the only AC, not DC. Okay. So to convert this AC to DC, we need to use one rectifier. So here I am taking the one diode bridge rectifier. Why rectifier? To convert AC to DC, we must need a rectifier. But in rectifier, you are not getting the pure DC. You will only get the pulsating DC. To convert this pulsating DC into pure DC, you need to connect the some filters. You need to connect the passive filters like LCL filter, LC filter like this. Then only you will get the pure DC. So after that, you need to connect the one power factor converter, nothing but the boost converter also here, because to meet our DC link voltage. So here this is the point of common coupling. Here we need to connect this grid as well as this solar system because these two are sources to our induction motor, right? So to connect these two, we need to have same powers. Here we are getting the DC and here we are getting the AC. We don't connect different sources, right? We need to connect only same sources. That's why here first of all I need to convert this AC to DC by using diode bridge rectifier. But in this rectifier we are not getting the pure DC. We are only getting the pulsating DC. So to convert this pulsating DC into pure DC, we need to take the filters. So here I am taking the passive filters, LC filter, and after that we need to give to the one boost converter, nothing but power factor converter, to meet our DC link voltage or our load value. After the boost converter you are getting the DC, right? So here also after this boost converter you are getting the DC. So this is DC and here also we are having the DC. So you can easily connect these two here. Okay, now you can give it to the 3-phase inverter, then this inverter converts this DC to AC and we can give it to the induction motor. So this is the whole process of our project. So here main thing is the power is transferred from this solar system and this grid. So we can share this power depending on load requirement and depending on solar condition, like that. Whenever the solar is completely off, nothing but at night time, we can only depending on a grid. In afternoon time or evening time also we are not getting the exact power from the solar cell. So in that time also we need to depending on the grid. So like this we need to transfer power from this solar cell and grid to our load, nothing but the induction motor, in thinking manner. That is nothing but the intelligent manner. Okay, so that power sharing is very important. So that's our title. So now you can easily understand our project title, that is nothing but intelligent grid interfaced solar water pumping system. That is our project title. So here what we are interfaced, we are interfacing grid with the solar, right, to our water pumping system. Water pumping system nothing but this induction motor. Okay, and I also told you the power sharing between these two is very intelligent manner, means thinking manner. Okay, so that's why I'm using the word intelligent. That's why our title looks like this. That is nothing but intelligent grid interface solar water pumping system. That's it. I think now you can get the clear idea about your title, nothing but the justification, how you can justify your title like this, you can say at your presentation. Okay. Now just look into the circuit diagram. This is our main circuit diagram of our project. So here just what I explained before, that only they given here. So that is nothing but they are taking solar power here, and after that they are taking boost converter with MPPT, right? This is the MPPT boost converter to get the maximum power from this solar system. Okay, so here also you are getting the DC, and after the boost converter also you are getting the DC. But our induction motor requires what? This requires AC, right? So to convert this DC to AC, they are taking the inverter. This is the three-phase inverter. Okay, so this three-phase inverter can convert the DC to AC. So then you can give it to the our induction motor. That's it. And coming to the alternative source, that is nothing but the grid. Here I am taking to the towards AC grid. So the name itself indicates it is the AC, right? But to connect this AC to our solar system, you need to convert this AC to DC, right? That's why I'm taking the diode bridge rectifier here. So this diode bridge rectifier can convert this AC to DC. But at the bridge rectifier output, you are not getting the pure DC. You are only getting the pulsating DC. So to convert this pulsating DC into pure DC, we need to get the some filters. So this is the LC filter I am taking here, nothing but the passive filter to converting the pulsating DC into pure DC. So then only we need to give it to the another boost converter. This is nothing but the power factor converter for our grid to meet the our load requirement. Okay, so after the boost converter you are getting the DC. Now you can connect this DC to our output of the solar system DC, because now this is DC and this is also DC, so you can directly connect these two. Okay, so here I'm taking the some DC link capacitor. After that this DC is converting into AC by using three-phase inverter, and you can give it to the induction motor. This is the complete circuit diagram of our project. And here I am operating this circuit in three different modes. We have three modes. In first mode of operation, I am taking power from only this solar panel. So here I am taking the power from this solar panel to our induction motor. So here load required power is only taken from the solar system. So solar system has enough power to run the motor. So that is the first mode of operation. Here only solar system, nothing but the PV system is turned on. Okay. And coming to the second mode of operation, the power which is required for induction motor is taken only from the grid. If you take the night time, during night time solar does not generate any power, right? So to run the motor in the night time, we need to depending on the only grid. Okay, so the power which is required for the induction motor is only taken from the grid at night time. So that is the mode 2. So in this mode only the power is taken from the grid. And coming to mode 3, in mode 3 I am taking power from the grid and also power from the solar system. Why? Because I already told you in daytime also, in cloudy day, we are not get the sufficient power from the our solar panel. So in that time also we need to require more power from the other source. So at that time we need to take power from solar system and also take power from the grid system. So that's why the power is sharing between these two. That is the mode 3. In mode 3 we need to turn on the solar system and we need to turn on the grid also. So this is the three possible conditions I am having for our project. And the next thing is, here we are having the switches set every condition. In inverter we are having the switches, right? Nothing but IGBT, MOSFET, whatever it may be. So we are having the switches. So S1, S2, S3, S4, S5, S6 like this. They are fully controlled switches. Fully controlled means they can turn on, they can turn off by ourselves. Okay. they are not like diodes, because if you take the diode, you don't need to give the triggering pulses. It can on whenever it is forward bias, it can off whenever it is reverse bias. But these fully controlled switches like IGBT MOSFETs are not like that. We need to give the pulses to turn on, to turn off. Okay, so that pulses is mainly depending on the control system, because in grid system you are having the one switch in power converter, right? And this inverter also you are having the 6 switches. So these all switches can control the power flow, and this solar boost switch is completely different because that is used for maximum power point tracking. Okay, these both are different. They are simultaneously operate that maximum power point tracking and boost converter, but this grid connected boost converter and this inverter need to controlled by some parameters like load value and source values, like that. That means whenever you have the switches like IGBT and MOSFET, so to turn on, to turn off that MOSFETs and IGBT, you need to give a switching pulses like this. Okay, you can see in your academic, this is the gate pulses to your switches, like on time, off time, again on time, again off time, on off, like this. You can give pulses like this, then only it can turn on, it can turn off. Okay, so to generate these pulses we have pulse width modulation technique, PWM techniques. So in that PWM techniques we have so many. So here I am using the sinusoidal pulse width modulation technique in our project. Okay, because that is very simple and that is very easy to generate. Okay, the main process of sinusoidal pulse width modulation is, the name itself indicates the sinusoidal. Means in sinusoidal pulse width modulation we have two waves, that is nothing but the one is reference wave. Always sine wave as reference wave in sinusoidal pulse width modulation. That's why that name indicates sinusoidal pulse width modulation. And you can take the another wave as whatever you want. You can take triangular, you can take trapezoidal, you can take sawtooth, whatever it may be. Okay, you can take the carrier wave like this. Okay, this second wave is nothing but the carrier wave. So in pulse width modulation we can give the conditions. Here whenever the carrier wave is greater than the reference wave, then we can turn on the switch. This is the first condition I am giving. And second condition is, whenever the carrier wave is less than the reference wave, then we need to turn off the our switch. Like this you can give the conditions. So here if you take from 0 to some t1, time t1, so at this time, is it reference wave is greater than or carrier wave is greater than? Obviously carrier wave is greater than, right? That is more. So first condition is true, then switch will be on. So during 0 to t1, switch 1 will be on, right? Switch will be on. And during next time interval, during this point to this point, is it reference wave is more or carrier wave is more? Obviously reference wave is more. Means second condition is true, that is nothing but the switch is off. Okay, and next interval again carrier wave is more, again switch will be on. Okay, again off, on, off, on, off. So like this you can generate the your switching pulses. In our project we need to get the two values, that is nothing but the reference value and second one is carrier value. So how we can get these two values? From the control system you can get that these two values. If you take any control system, that will be like this only. You can take some positive here and some negative here, and you can give it to the some PA controller, PR controller, whatever it may be, and give it to your switching pulses, nothing but on off like that. Okay, so here this is the reference value you can get here, and we need to take the one carrier value, that is nothing but you can take the another separate block like sawtooth or carrier wave, like that. Then you can give it to the one less than greater than conditions and give it to switching pulses. Okay, this is the common control system blocks. Okay, so here in positive you can take it as a reference value, and in negative you can take a actual value. Reference value is nothing but whatever you want at load. Our motor rating is 240 volts AC, then that is the reference value. And what is the actual value? The actual voltage you are getting at that point. Means at morning 9 a.m. whatever the power you are getting from the solar system, that is the actual value. It's 100 volts, but you need 240. So this is plus and this is minus. Then you will get the 240 minus 100. The error is 140. So here you are getting the error value is 140. So then this PA control will be tell to our system, because you are not getting the exact voltage, you need to depending on another sources. So here grid will be on, that remaining voltage will be taken from the grid. So like this the control system will be operate. So at another condition, at 12 o'clock, if you get the exact power 240 volts, so at that time here this is 240 volts and actual voltage also you are getting the 240 volts. So here you are getting the 240 volts, error will be 0, right? So here you are not getting the any error, means you are getting the exact power which is required for your load. So here no need to depending on this grid. Okay, so like this, with the help of this control system, you can control the whole system. Here I am taking only voltage for example, but like this you can control the current also. Okay, so let's see our complete control diagram. So this is the our complete control diagram for our system. So here you can use scalar or voltage frequency control algorithm. So just before I explained for only voltage, so like this they are also taking the voltage VDC reference and VDC actual. Like this they also take the current IL reference and IL actual. Okay, and give it to the PA controllers. So this is the PA controller I am taking here, and this is the another PA controller I am taking here. Okay, and we will give it to the one pulse width modulation generation, nothing but this is the carrier wave. I already told you this is the carrier wave. You can take sawtooth, trapezoidal, triangular, whatever it may be, and this is the actual value we are getting, nothing but the reference value. Okay, and this is the carrier value. So we can give it to the less than greater than condition, and we can turn on and we can turn off the switches. That's it. Bottom also you can generate the pulses. So here I am taking the solar panel voltage and solar panel current. I am getting the solar panel power because we know the P is equal to V into I. That's why I am taking voltage and current and I will give it to the multiply operator. Then you will get the PPV. So solar panel power I am getting here, and this is the I am taking as the reference, and here I am taking this is the actual. Okay, and again I am giving to the sinusoidal pulse width modulation, and I am generating the switches for our inverter. That's it. This is the simple control technique I am using here. Okay, and if you want to design this project in MATLAB, you need to get the parameters. So here we have the input voltage Vs and LF and CF and VDC and CDC. So like this they have some parameters. So first of all you need to get these values, then only you can design your circuit. Okay, so how to calculate these values? I will provide the one table. So here is the our design parameter table. Okay, so here first of all you need to generate the reference DC power. So this is the VDC reference because it has the star mark, right? So we know the expression VDC is equal to 2 root 2 VLL by root 3. We know the VLL is nothing but the grid voltage is 230 volts. I already tell you. Okay, so if you take this VLL 230 here, this 2 root 2 into 230 by root 3, then you will get the 375.6 volts. That is the calculated value, and you can use that nearer value, round figure value 400 volts, like that. Okay, and coming to CDC, capacitor of DC. So this CDCs you can see in our circuit diagram. So this is the DC link capacitor. So this is the CDC, right? Here we have the CDC. So this value I am calculated here. Okay, so CDC formula is 6 alpha VLL into I of t by V reference square minus V actual square. So here we know the each and every value. Alpha is equal to 1.2. I am taking reference DC voltage we already calculated before here. This is the reference voltage I am calculating as 400 volts. You can take 400, and VDC actual as 375, and line to line voltage is 133, and I is equal to 8.3, and T is equal to 0.005 seconds. So if you take all values in this equation, then you will get the 2051 microfarads. So you can take the 2200 microfarads. Okay, this is the capacitor of DC link. And coming to the DPV, we know the formula D is equal to VDC minus VMP by VDC. So we know the VDC values just now we are calculating 400 volts. You can take the 400 volts, and VMP is 315.7 volts. So you can take these two values here, then you will get the 0.21. And coming to the LPV, so this is the inductance of solar panel. So that inductance of solar panel you can get the VMP into D by delta I1 into Fs. So we know the each and every one here, that VMP value, VD value, and delta I value. You can put these values in here, then you will get the 4.52 millihenry. So you can take the 5 millihenry in our simulation block, then you will get the inductor value. So here we have the LPV, right? This is the LPV value. And coming to the grid side inductor, this is the formula. So like this, each and everything I will provide you, don't worry. So I will give this base paper in the description. You can download it. So in that you can get the each and every value like this. Okay, I will give in the description, don't worry. Okay, like this you can calculate the each and every element value. Okay, and coming to the solar power designing. So you need some parameters to design the solar panel also. And this is the table for solar panel designing purpose. Okay, so here they are giving the parameters and specification also. Okay, so here the maximum power module is 210 watts and open circuit voltage is 35.7 volts and short circuit current is 7.99 amps, and they given the number of modules connected in series and parallel is 11 and 1. Okay, and then they given the voltage and current of solar power array at maximum power point tracking is 315.7 volts. You can get that maximum power point, and 7.32 amps you can get at maximum power point. Okay, and they also given the maximum power of SPV array, that is nothing but the 2.3 kilowatt. So like this they given the each and every parameter of solar panel. So by using this you can easily design your circuit. Okay, so now you can see the results. After doing this project you can get the results like this. These are the starting characteristics of a solar pump in mode 1. We have 3 modes, right? So in first mode I already told you only solar cell is operate. Here grid is completely off. Okay, that's why you can see grid voltage and grid current is completely zero. So these two are the grid voltage and grid current, they are completely zero, because in mode 1 only you can get the power from the solar. We are not getting the power from the grid. Okay, so that's why here grid voltage and grid currents are zero. And you can see the motor is started in soft manner to limit the starting current. So the motor is starting, this is the speed of the motor, is starting in smooth manner. So after it will be get at 1200 rpm. The reference speed is calculated by the control scheme. So at 8.6, so this is the point of 8.6 seconds. So here VPV IPV are settled to their maximum power point tracking. So here only the IPV and this VPV you can get the maximum power. So here they are steady state. So up to this value it will be increasing, right? This voltage and current of the solar panel is increasing. So at some point it will get the maximum power. So at this point only it will be steady state. That is the 8.6 seconds time. Okay, and the DC bus voltage is maintained to the constant value, that is nothing but the 400 volts. Okay, this is the 400 volts, we are maintaining the constant value. And coming to the dynamic state, so this is the steady state. And coming to the dynamic state, how it will be? So this is also mode 1, but here we are taking the dynamic state. So I already told you in mode 1 grid is completely off, such that Vs and Is is 0, because here we don't turn on the our grid. We are only depending on our solar system. And this is the G, nothing but the radiation of the solar system. This is the voltage, this is the current, and this is the power of the solar. And this is the DC link voltage, and this bottom are motor current, motor speed, and motor torque. So I am telling you this is the dynamic state. Dynamic state means the name itself indicates it will be changing with respect to time. So here the slope is decrease in radiation is observed at t is equal to 2 seconds to 3 seconds. So this is the 2 to 3 seconds time. Here you can observe the slope is decrease in radiation from 800 to 400. So here this point is 800, and here the radiation is decrease 800 to 400. Again 3 to 4, again radiation is increased to 400 to 800. So like that it will be changing with respect to time. Okay, so with the decreasing in the radiation, the current of the solar system is decreases, as well as the motor speed also decreases, and again the irradiation also increases, solar current also increasing, and the speed of the motor also increasing. That's it. These are the characteristics of dynamic state in mode 1. And coming to mode 2, these are the mode 2 characteristics. This is also steady state performance. So here I already told you in mode 2 only grid is connected. Here completely solar system is off, because you can take it in night time. Here in night time we don't get the power from the solar. That's why the complete irradiation and solar voltage and solar current and solar power all are 0. So why? Because here we are taking mode 2. In mode 2 completely solar system is off. That's why you are not getting anything from solar. But you can get the DC link voltage as 400 constant, because you can take power from the grid. So this is the grid voltage and this is the grid current. So here grid will be on, right? So I already told you grid in AC format. That's why you are getting the AC voltage and AC current like this. Okay, and this is the current of the induction motor, and this is the speed, and this is the torque. This is the steady state condition. That's why it is not changing with respect to time. It will be constant. Okay, all time. That's it. This is the mode 2 operation. And coming to mode 3, so this is the mode 3 dynamic operation. So here in mode 3 I already told you both PV and grid will be connected. So that's why here we can get the power from the solar and you can get the power from the grid also. Okay, so here you can observe from 2 to 3 seconds again irradiation will be decreasing and also current will be decreasing, and also here during 3 to 4 irradiation will be increasing and also current will be increasing. But at this mode it can't affect the motor speed. Motor speed is always constant because here the remaining power is taken from the grid. You can observe here from 2 to 3, whenever the current is decreasing from 2 to 3, then here the current of the grid is increasing, right? So that is covered here. So whenever the current is increasing from 3 to 4, that is covered here. Here grid current will be decreasing, right? So it can be effect on the motor. Always motor speed will be constant. That is the use of power sharing between the two sources. And whenever you can get the constant voltage, then our waveform will be constant. Whenever the changes will occur, at that time only current is changes, but our speed will be constant. That is the main thing you need to know. And this all are came due to that control block only. Whenever the current and voltage changes, then we can need to change the step size and we can keep constant our motor speed. That is the main thing you need to know. Okay, now let's design this circuit in MATLAB. Then you can observe your waveform, whether it is coming like this. If it is come like this, then only you can successfully done your project. Now let's connect circuit in MATLAB. Actually our circuit is like this only. So whatever I'm showing here, that only I'm connecting in MATLAB. Now open your MATLAB. This is the MATLAB circuit for our project. Don't panic about this. Just remember what I told before. That only I'm designing here. So here first of all we need to take the solar panel. That's why I'm taking the PV array here, and this lookup table will be the irradiation, and this 30 degrees block will be the temperature. Here I'm taking the 30 degrees temperature, and this G will be the irradiation, the value which is came from this lookup table. Okay, and next thing we need to give this solar output to the boost converter. That's why I'm connecting this solar output to the this boost converter. This simple inductor and IGBT and this diode make a boost converter. I already told you this boost converter with MPPT will use simultaneously. So here I am taking the maximum power point tracking. That is nothing but the incremental conductance I am taking. I already told you the advantage of incremental conductance. So here the input of the incremental conductance will be VPV and IPV. That is nothing but the output of solar panel voltage and solar panel current. The two values will be taken from here, VPV and IPV. Here we have some measurement port, right, in solar panel. So from this measurement port you can take the voltage and current. After taking the voltage and current values, you can give it to the MPPT algorithm here. Then you can get the pulses to our boost converter switch. After that, actually here we are getting the DC, but our load nothing but our induction motor. This is the induction motor. This induction motor need AC, right? So to convert this DC to AC, we need a inverter. That's why I am taking the inverter in between this boost converter and our induction motor. This is the three-phase inverter I am taking because our load is the three-phase induction motor load. That's why I am taking the three-phase inverter here. These 6 switches will make a three-phase inverter. Okay, with the help of some DC link I am connecting this, and I am measuring the voltage and currents in voltage measurement and current measurement. So here I am taking the voltage measurement here to measure the DC link voltage across this capacitor. So we already know in our laboratory how can we connect voltmeter. We are connecting the parallel, right? So here also I am connecting our voltage measurement in parallel to our capacitor. Okay, if you want to measure the current, you can connect the current measurement in series because we connect the ammeter in series in our laboratory. So like that you can take the current measurement and voltage measurement like voltmeter and ammeter. Okay, for single phase measurement, this voltage measurement and current measurement. But if you take the three phase, here the output of this inverter will be the three phase AC, right? So how to measure this three phase AC? So that's why I'm taking the three phase VA measurement block here. This is the three phase VA measurement block. If you double click on any block, then you can know what it is. Okay, this is the three phase VA measurement, nothing but the voltage and current measurement. Okay, so this one simple block can measure the three phase voltage and three phase current. No need to take voltage measurement and current measurement separately. If you want to measure this three phase voltage with the current measurement and voltage measurement, you need to take the current measurement for each phase. Here we have the three phases, right? A phase, B phase, C phase. So you need to take the 3 voltage measurements and 3 current measurements. That will be the complexity, right? So that's why we have the inbuilt block, that is nothing but the 3-phase VA block in our MATLAB. So you can take this one, then you can measure easily. Okay. So after conversion of AC by using this inverter, you can give it to the directly our induction motor. That's it. Here I am using the torque 15. So this TM terminal means the torque of the motor. Okay. And finally here we are measuring the motor speed and motor torque. And coming to grid part. So this is the grid part. Here you are taking the VAC, nothing but the voltage of the grid, and give it to the diode bridge rectifier, because this grid means the AC. But to connect this grid to our solar system, output of the solar system will be DC, but this grid system will be AC. So to meet these two, we need to convert this grid AC to DC. That's why I'm using the diode bridge rectifier here. This is the diode bridge rectifier. So to measure the voltage and current, we need to take the voltage measurement and current measurements here. I already told you this is the current measurement. Here we are connecting in the series. This is the voltage measurement. We are connecting in the parallel to measure the grid voltage and grid current. So this Vs means the grid voltage, okay, and this Is means the grid current. Okay, like that you can take. And after that, output of the diode bridge rectifier, we are not getting the pure DC, we are getting the pulsating DC. So to convert this pulsating DC to pure DC, you need to take the passive filter. Here this LF and CF can make the passive filter, then you can get the pure DC. So after that, you need to give it to the another power factor converter, that is nothing but the boost converter. Here this inductor, this switch and this diode make the grid side boost converter. Okay, then you can get the DC here and give it to the inverter to convert the DC to AC and give it to the induction motor. So like this you can connect, and the remaining part is control part. In bottom you can get the control part. Here I already told you we need to take some reference values and actual values. So here 400 is the reference value and this VDC is the actual value. We can give it to the PA controller. So like that you can control the voltage and current also. Here also you are taking the IL, and here also you are getting the some reference value and give it to the another PA controller and give it to the switching conditions like less than and greater than with the help of this repeating sequence like carrier wave. Now you can give it to the your switches like S grid. S grid means this is the power factor controller switch, grid side control switch. Just double click on this one and click on this blue name, then you can get the where it is came from. So this is the boost converter of the grid side. So here we are giving the pulses like this. I already told you before, this complete control system. So that only I am designing here. Okay. So here also I am getting the VPV, IPV, and again we need to give the some reference value and actual value here, and again some controller. So like that you can get the, for this 6 switches also you are getting the pulses. That's it. This is the complete circuit diagram. And coming to scope, the scopes are used for to see the waveforms. Actually this is the figure for only first mode of operation. I already told you first mode of operation is only solar panel is working, grid is completely off. So for second and third mode of operation also I am having the another 2 files, but this is the only for first mode of operation. So let us see how this first mode of operation and how the results will be. These are the VDC means DC link voltage, and VS means grid voltage, IS means grid current, like that I am taking, and IABC means 3-phase current that is came from the 3-phase inverter, and this is the motor speed and this is the motor torque. So like that I am taking to see the waveforms of each and every value. Okay, now run your circuit. After completion of running, just open the scope blocks one by one. So first of all I need to open this one, first one. So here I am getting the results like this. This is the results I am explaining before. Okay, exactly we are getting as per base paper. Actually the x-axis value will be 18 because I am taking the 18 here in simulation time. Okay, that's why I'm getting the x-axis will be 18. That is nothing but the in this 18 seconds from 0 to 10 it will be the steady state operation, and 10 to 18 it will be the dynamic state operation. Okay, now open the scope. Now observe from 0 to 10 from this line only it will be the steady state operation. So that's why we are not getting the any deviations in this steady state operation. Okay, it will be simply go to the maximum power point at 8.6 seconds, then it will be the steady state. But during 10 to 18 seconds it will be the dynamic state. So during 10 to 18 you can able to see the decreasing and increasing in the irradiation. So if irradiation is changing, then our current also changing. Okay, like that. So like this you can observe the graphs as I said before in theoretically. Okay, now next scope is for DC link voltage and for grid voltage and for grid current. I already told you this diagram is only for the first mode of operation. So in first mode of operation grid will be completely off, right? That's why we are getting the grid voltage and grid current will be 0. So this 0 and this 0, that is the grid voltage and this is the grid current, because in first mode of operation grid will be torn off. Okay, we are getting the sufficient power which is came from the solar panel. Okay, but the DC link voltage will be constant because we are getting the power from solar panel, then that will be the constant voltage, nothing but the 400 volts we are getting. And coming to next one, IABC and speed and torque, that is nothing but the 3-phase current, speed and torque of the our motor. Just double click on the scope, then you will get the 3 results. So these are the results we are getting. We already know from 0 to 10 it will be the steady state operation. That's why it is starting slowly. Then at 8.6 seconds we are getting the maximum power point, right? So that's why here at 8.5 seconds it will goes to its maximum speed, that is nothing but the 1200 rpm we are getting. So from this it will be maintain the constant speed. Okay, but we know from 10 to 18 it will be the dynamic state. So in this state we are getting the different irradiation, then we can get the different speed values. That's why it is reduced here and increasing here. So like that you can get the changes in dynamic state. That's it. These are the waveforms we are getting. So like this second and third mode of operation also same circuits, but the only thing you need to change is that mode of operation. That's it. In this mode solar is on, right? So in second mode grid will be on, then you will get the solar voltage and solar current will be 0. Okay, like that. In third mode of operation you can take the grid and solar also. Okay, so we can power our load by using grid and solar as well in third mode of operation. Like that we are having the 3 phase. So this is the complete project. So if you want this project, then contact me. I will give you, and I also provide the base paper of this project in description. You can check it once.